All right. Welcome back, folks. Is my video showing?
It is.
Okay, excellent. I can't see myself. It's very disconcerting. I forgot to make my silly joke about how I was at APL yesterday and now I'm on the moon. So I will say it now and hopefully everyone will groan and then we'll move on. So, all right. We're glad to have everyone back. I hope everyone had a good time in the in GatherTown and got to have some good discussions going on. We may try to do some of those more frequently just for networking in the future. If you liked it, make sure you let me know. All right. So our next panel will be the Awardees and Partnerships panel, which is going to give you a little bit of a taste of some of the projects that have been awarded by Space Technology Mission Directorate. So I'm going to pass it off to Dr. Dana Hurley, who will moderate that panel. And we look forward from hearing from all the speakers. Thank you.
All right, thanks, Rachel, and welcome everybody. Good afternoon, good morning, depending on where you are. One note I want to make is with apologies, there was one speaker that was omitted from the program for today's session. So Christian Hawat from MIT is part of this panel, and so there will be 8 presentations. So panelists, you'll have 5 minutes to present, followed by 2 minutes to field questions. So also feel free to answer questions in the Q&A panel after your presentation. So audience, when you have questions, go ahead and enter those into the Q&A panel so that they'll be all queued up at the end of the 5-minute talk so we can ask those of the speakers. And with that, I'd like to welcome our first panelist, Dr. Christine Edwards from Lockheed Martin. Christy, you ready to go?
Sure.
All right, great, thanks.
All right, I'll share my screen. Here we go. All right. So hello, I'm Dr. Christine Edwards, the Deputy Exploration Architect at Lockheed Martin Space. My team looks at the kinds of missions that NASA, industry, and our international partners want to perform in the future. And we develop concepts, early system designs, and technology demonstrations that could help accomplish those missions. Today, I'll be discussing 2 of our lunar demonstration projects. One is the vertical solar array technology, VSAT, with NASA's STMD's game-changing development program. And the other is the cryogenic demonstration mission, or CDM, with Tipping Point. First of all, though, as a systems architect, I wanted to set the stage on what the initial lunar infrastructure could look like that could utilize the technology in these demos. So after the first mission, with the first woman and first person of color to land on the moon, subsequent crewed missions could occur on a cadence of every 2 years. Exploration support will include an unpressurized rover, pressurized rover power elements, including a VSAT, providing supplemental power for the rovers and enabling for crew habitation. And ISRU investigations can include Viper, regolith O2 extraction, micro PSR water extraction. And then later on, fission surface power could provide additional power that is steady through the lunar night. And an ISRU pilot plant could begin production. So this was the slide that I presented earlier for the lightning talk. So this time I just want to highlight how this figure illustrates how these elements can support a mobile architecture for exploration missions that would go to various locations around the South Polar region, and then form part of the Artemis base after a site is selected, and then also adapt to incorporate new technologies that are being developed across the industry, like an ISRU plant and power beaming into craters. So one of the Lockheed Martin demonstration missions is our VSAT solution. We are one of the commercial companies that NASA is working with to mature vertically deployable solar array systems for the lunar surface. It's part of the game-changing development program. Lockheed Martin's concept for VSAT is an operational system that combines innovative modifications to existing solar array technology with deployment and retraction mechanisms, and a composite mast design with leveling legs and a gimbal. This system can provide reliable, sustainable power to support other lunar elements like habitats, rovers, ISRU systems, and construction systems. And our anticipated commercial impact is to help reduce the barrier of entry for lunar surface assets by providing power. So they don't need to generate as much power themselves, and to help other elements survive the lunar night. Another technology demonstration that we are developing is the Cryogenic Demonstration Mission, or CDM. This demonstration is being developed with Tipping Point, and we will complete an in-space demonstration mission using liquid hydrogen that tests more than a dozen cryogenic fluid management technologies. And these fluid management technologies that are tested with this mission will enable better handling, transferring, and storing of cryogenics that are produced by ISRU. I just want to end with that these are really exciting times to be living in the Artemis era of space exploration, and to get the opportunity to contribute towards these missions. Working on these kinds of demonstration missions helps to advance these key technologies that can enable these visions for sustainable lunar presence. Thank you.
All right, thank you very much. So if there are questions, please enter them into the Q&A. I don't see any, so I hope I'm actually seeing the right Q&A. But I have a question for you. So, you know, for commercial provider or commercial companies out there, or other people who would like to use the VSAT and the microgrid that you're working on, you know, what do they need to do to understand how they could connect to it and how much power they could be supplied by the efforts that you're doing?
I know that one of the some of the work to go is to define those kinds of interfaces, and we're also gathering information on what the power needs are for the elements that'll be going to the moon. So in the poster that I shared today, I have an estimate of like what the power demands could look like. So getting to know what others' power demands could be can really help with setting up what the interface will be. And then also we're working to the requirements that that NASA has talked about of providing, I think it was 10 kilowatts as the goal.
Okay, great. Well, that's exciting. Okay, thank you.
Thank you.
Our next speaker is Dr. Alian Wang from Washington University. Alian, are you ready to go?
Yes, I'm ready. Let me share my screen.
All right, thank you.
Can you see the screen?
Yep, we see it.
Okay, so we are funded by NASA LuSTR project. Our project name is Volatile, which is a lunar subsurface volatile detection. Our team developed a variety of sensors. So this is our effort to develop. This is our effort to develop LIPS system, which will detect the hydrogen, which is the water or OH in the lunar material, to quantify it and also to find the spatial distribution of those material. Our goal is in the right part of the table to detect the water content at 1% of the volume. To have the spatial resolution in the depths smaller than 1 centimeter. And we have the very quick recording system And so we can do very quick measurement, and we have small footprint, assuming we are targeting to a small footprint of 3 kilo. So our team is organized by scientists like myself, is a planetary spectroscopist. Our co-I, Brad Jolliffe, is a lunar scientist. And our engineering team is in impossible sensing, who developed a lot of different type of instrument sensor. And we are consultant by Honeybee mechanical engineer for the drill. And the critical part is that we are going to put a very tiny ellipse probe into a drill bits. And you can see in the image, the blue circle is the window of our ellipse probe. So it's about 5 millimeter in diameter and smaller than 5 centimeter in long. So in comparison with the whole drill bits, our goal is to detect a variety of elements, including the hydrogen peak. You can see that LIPS is able to detect the hydrogen. So lunar volatile is our goal. The challenge of our technology is to combine the laser excitation for LIPS and the LIPS spectral collection into one optical path. So we put that is the two excitation in the blue, in the red and the green part, and the collection in the collection path illuminated as the blue. So on the right side, you can see a very tiny laser crystal target tapped on the end of the fiber. And actually we can generate a small spark, which generates LIPS signal from the lunar soil. So that is the first bidirectional microchip architecture as a LIPS, and also LIPS in the drill bits technology. And we are targeting to develop, design and develop the first breadboard in year 1. And in the year 2, we are going to assembly and miniaturize the system and test on the real lunar regolith simulant and related material to reach TRL4 in 2022. Then in the same time, we're going to design the TRL5 prototype against an existing drill, which is made by Honeybee, and a commercial clip rover as notional spectrograph, spacecraft. And we're targeting more higher TRL to 2020, assuming we can win another competition to move forward. So another two technology I would like just to present is that we develop under NASA's support currently on survey and WashU research funding. So we develop a small IR system which have extremely small mass volume and power. Currently TRL 5 to 6. We passed the radiation, passed the temperature, and all these tests, and got good spectra with the water ice mixture with the lunar simulant. And this can be deployed either by arm or by the wheel or by the by human, by astronaut, to just deploy it on the surface of the lunar regolith. Another sensor we are developing is the Raman spectrometer, which collaboration with JPL, currently under development for DALI and for IC. And our current team, including the WashU science team and the JPL and the Honeybee and the University Leicester in UK for the development. For lunar application targeted on general mineralogy, and also ISRU raw material on the product identification and the quantification. In addition, we have developed this instrument for Europa lander. That's all for my slides. Welcome for any question.
Great, thank you so much. This is exciting, and you know, I'm looking forward to seeing chances to deploy those instruments to try to understand the volatile content of the lunar polar regions. That's super exciting. Let's see. So there are no questions in the chat. I'll ask a quick one. You know, so how long do you think it would take to do one of the analyses to get the composition of the soil using the Wrangler?
The Wrangler is LIPS technology. So we normally get spectra in 1 second. And while we are drilled down to the regolith, we are going to keep taking LIPS spectra every 1 second, 2 seconds. So we get the spatial resolution in the lunar regolith at 1 centimeter or something. So the spatial distribution, I mean, at the surface, you may not get the hydrogen, but once you're going down, you can get more. And in addition, we get other elements.
Right, yeah, that's super exciting. Thank you very much. All right, so next we have Dr. Ahmed Chowdhury from University of Texas, El Paso. Ahsan, are you ready?
Yeah, I'm ready. Can you hear me well?
All right, great, thanks. Yep, go ahead.
Okay, so I'm going to try to share my screen and see what comes out good, okay? So double checking that you can see it well.
Yep, we can see. Thank you.
Okay. Hey, thank you so much for allowing me to share the new LuSTR project we are about to start. I'm Ahmed Chowdhury from the Aerospace Center at the University of Texas, El Paso. Our project has a couple of innovative niche, but it's attempt to address couple of gaps in the literature as well as demonstrating a system.
Oh shit! Then he needs that exam.
Okay, so kind of like the little project overview of this particular project. We are working on a comprehensive approach to collect the sublimating vapor from the thermal mining approach. So part of the reason is that unless you can hold pressure, you expect to have a low pressure environment when you use a thermal mining approach. So how to transport this vapor to the cold trap and then effectively use a cold trap to condense that ice, collect ice, is a technological challenge that hasn't been fully addressed. Also, there is also a big gap of understanding the thermophysical properties of lunar regolith. And that partly because that we don't have a whole lot of a study done to measure the thermophysical properties of icy regolith. And that will kind of dictate your design process of not only thermal drill, but all the subsystem associated with collecting the low pressure vapor, and as well as use them effectively collect ice. So that's kind of challenge. So in this little cartoon shows what exactly we're attempting to do. So our approach is in the thermophysical property measurement side, we are trying to measure the specific heat and thermal diffusivity for lunar regolith at a wide range of conditions. So we're not fully the composition of icy lunar regolith and their physical form is not fully known yet. So we would like to do a range of study of seeing at different conditions to measure specific heat and thermal diffusivity. The parameters very, very important to actually design not only thermal drill, all other subsystems. Would like to also do a kinetic study to energy of water sublimation from different types of icy regolith. All those things will fit the design process, and then also find some of the delamination rate of ice from the cold trap, which I'll talk a little bit later. So this is overall, we have a dirty thermal pack and all other equipment necessary to do the project. One of the larger challenges you to understand, so when you put a thermal drill, is a thermal trend or something, you have a very low pressure vapor. How are you going to collect the vapor and direct them to your cold trap? So our approach to using is called ionization technique. So we are experimenting with ionizing the sublimating vapor, low pressure vapor, either DC, RF or other magnetic trapping, and then guide them through the cold trap. Has two advantages. One, the separation is done by default when you ionizing the sublimating vapor. So you don't need a separate separation process of water with other volatiles. All will need to be seen that what's the power requirements of it and whether that makes sense, whether you can effectively ionize that. So that's part of the larger goal of the project. Second, obviously you take those vapor and then using a cold trap. So we are attempt to do a very effective cold trap. So when you start to collect ice on your cold trap, if you don't delaminate them, they will lose effectiveness. So engineering solution has to be developed that will allow you to effectively delaminate the ice and continuously to collect it. Our end product of this is to really do a integrated system from thermal mining, ionization-based vapor transportation and separation, collecting ice on the cold trap, delaminate them. So this is, we would like to demonstrate a kilogram level ice production. So we did some estimation and we saw that some lab scale work and some other analysis that we could actually increase almost 450% of water collection. And we'd like to take the technology, whatever we have done so far, analysis and preliminary lab scale work to TL5 level systems. And we have a project collaborator, Extraterritorial Resources, who are overseeing a system level analysis of this particular technology. So we have do some analysis so that in 30 minutes, a flat heat pipe with 12 inches square feet can really collect. So if you run over a year, it can produce a 9 ton of ice per year. So this is some preliminary data. So this is kind of like an ice regolith. It's a JSC simulant and showing that the ionization of sublimating vapor. So this is kind of like, so we did a lot of work on creating the IC regolith. There's a lot of preparation involved with that, with a lot of help from NASA Johnson Space Center team. And right picture shows some of the sublimation out of the lunar regolith. Our preliminary work in last few weeks showing that ionization of the vapor and also having ice thickness of ice on the cold trap per hour. I think this small video of showing that we're delaminated. So this is a cold trap. Ice is collecting on the cold trap, and our technology allows us to delaminate and collect the ice on the bucket. So this is very quick overview of the project. The project started on May 10th. So just to show our overall summary, we're experimentally measuring the thermophysical property of IC regolith. Characterize the thermally assisted sublimation technology for IC regolith, effectively transport rarified water vapor to cold trap using vapor ionization and electric field pathways, and demonstrate efficient ice collection in a high capacity lab scale engineered cold trap prototype. That is our project. So I'm going to stop share and go back to happy to answer any question you might have.
Great, thank you so much. So, you know, this is a really interesting concept, and when you have icy regolith on the moon, there's going to be different kinds of ices mixed in there. What is your thinking in terms of when that separation occurs in your process? Is it through the thermal heating? Is it through the ionization process? Is it after you collect it?
Obviously, there's collection process in a low vapor environment. Either you use thermal drill. Also, there is a technology you're working with NASA Johnson Space Center called Lunar Agar. So it is a continuous feeding process of agar. In both processes, develop vapor mixed with ice and other water and other volatiles. And then the technology will to ionize that vapor, okay, and selectively remove water from it. So rarefied vapor, you ionize them, and then very similar to actual electric propulsion system, you just guide them to the cold trap, only water. Theoretically, that's the tech. We have some preliminary demonstration. That's why we wrote the proposal and got selected. But the full scale demonstration is part of the lab scale. Full demonstration is part of this effort. So once you the vapor out from the thermal drill or any other technique at low pressure rarefied environment, you ionized it.
Great, thank you. Okay, so next we're going to have Dr. Mihaly Horanyi from University of Colorado Boulder. Mihaly, you there?
Yes, thank you.
All right, great. Thanks. Go ahead.
Oops. Can you see my screen?
Yes.
All right, thank you. So this is an award about modeling lunar dust behavior to advance the effectiveness of dust mitigation techniques, which is a mouthful. But these projects started many years ago in our lab, and they were motivated by old observations that somehow remained unresolved, like the lunar horizon glow that was first reported by the surveyors looking west. After sunset, this bright cloud emerged. Whether it was always there or just the illumination conditions were right, we don't really know, other than the best guess about how they come about on an airless body like the moon was electrostatic processes. There are many other examples. For example, the dust ponds on an asteroid, which is very flat surfaces, indicating dust mobilization and transport without air, or winds or wind, again indicating electrostatics. And of course, a lot of issues about dust and dust clinging to surfaces were recognized as a technical and health hazard when astronauts were on the moon, making it really difficult to return to the cabins or working in a very dusty environment. So dust charging and mobilization and transport as a natural process and also as a process influencing the ability of astronauts living and working on a lunar environment. They somehow have the similar roots in the physical processes involved. So we are doing lab experiments for a long time, and this is one of the simplest setup. Imagine a vacuum chamber with a typical background pressure of 10 to the minus 5, 10 to the minus 6 atmospheric pressures. In the middle, there is a little tray that contains dust. Even though we are arguing about applicability to the moon, we like to use Mars simulants because they are red, easier to image. And then this little tray of dust can be exposed to UV light or a beam of electrons from above. And we can also generate a plasma environment having a beam of electrons below and then ionizing the background neutral gas. And then most of our observations are simply images using cameras. Just in recent years, the top left and the top right are animations, and I hope you could see them. The top left is slow motion, simply exposing the dust tray to UV light. There is no background plasma, there is no electron beam, just UV radiation. And surprisingly, reasonably big particles in our world, 30, 40, 50 micron sized particles are being lofted and swirling around in the chamber. So the left is a slow motion. The entire movie is only 3 seconds. On the right is a time-lapse image reorganizing the entire surface. In the lab, that little segment of a movie would run, the experiment would run for an hour. So that's kind of surprising that UV alone could mobilize dust. Even more surprising is after the UV exposure, we could take a biased grid and move it over the exposed surface. And notice that when the grid is positively biased or negatively biased, the outcome is different. So after UV exposure, that indicates that the dust particles are negatively charged. And that is weird, because all of you remember that UV exposure will generate the emission of photoelectrons that should leave behind positively charged particles. And then the recognition came that the charging involved here is not really a surface effect, rather than a volume effect, and the cavities in between the grains play a critical role of accumulating charges and eventually leading to Coulomb explosions. So photons or even electrons would find their way in between the grains and generate secondary particles, and those secondary particles will charge these cavities. And just because of the scale and the voltage difference, of course, is a couple volts, 2 or 3 electron volt on a scale over a few micron, indicating the emergence of enormous electric fields, small scale, but very intense electric fields that eventually lead to repulsion and mobilization of the dust particles. So that came to the recognition that you could use this, and maybe the easiest is to use an electron beam and shine an electron beam of various surfaces, let there be a solar panel or astronaut suit material, and the same process would liberate and remove dust particles. So we are kind of transitioning from a science application to a technology application to use electron beams to remove dust from surfaces. These electron beams are modest in energy, maybe 100, 200 electron volt, and the intensity is as high as you could make it, and seems to be very efficient of removing dust from surfaces. So these are the lab results and the possible transition from science to technology and dust mitigation technologies. But we are really somewhat short on a full theoretical understanding, and we are fortunate to get funding from NASA Early Stages Innovation Program last year to build up the numerical simulation capability of to follow these processes, which is a true challenge. Dust particles micron size in cavities, maybe a few micron size across, and then moving, in centimeter and meter scales. That is representing a tremendous challenge in connecting both spatial and temporal scales of many, many orders of magnitude. Perhaps 7 orders of magnitude go from a micron size, charging a micron size particle, and then making it move around in the sheath electric field, which is characteristically like a meter across. So there is a spatial scale disparity, as also a temporal scale disparity, as the mobility of electrons compared to ions is very large. And of course, the mobility of ions is still much, much, much faster than the mobility of dust. So we have kind of a subcycling in both temporal and spatial scale approach to connect up these vastly different scales in time and space, and hopefully be able to understand the details, suggest new laboratory experiments, and eventually optimize the technology that would allow you to use, for example, electron beam exposure to remove dust from surfaces on the lunar surface. And that's all I have for now. Thank you.
It's a wonderful example of using science knowledge to motivate technology development, and that's going to enable the further acquisition of science knowledge on the moon when we have things that can operate in the dusty environment there. So that's super cool. Let's move on. I think we're running a little bit behind. Our next speaker is Luis Maestro from Nokia Bell Labs. Luis, are you here?
Yes, I am. Let me share my screen.
Great, thank you.
All right, can you see the slides?
We see your PowerPoint, yep.
Okay, excellent. So first of all, thank you so much for the opportunity to present today. My name is Luis Maestro. I'm principal investigator at Nokia Bell Labs, and I'm going to talk about our Tipping Point Award for LTE proximity communications for future lunar missions. To kick off, why do we think that LTE and 5G wireless technologies are appropriate for space communications, and in particular for proximity communications? Well, to start with, because LTE is a very mature and proven technology with billions of subscribers globally. It's a technology that we use every day in our lives. Is continuously maintained and evolved in the standards. There is great support from infrastructure vendors, chipset makers, and O&M makers. So there is a lot of industry acceptance. There is a very well-defined evolution in the standards for these technologies in the 3GPP. If you have LTE today and the upcoming 5G deployments, the devices are backwards compatible, so you don't run into issues of getting some obsolete technology. Being all IP enables the possibility of integrating easily with other technologies and applications. It's a scalable and robust technology based on FDMA, which is a very well-known access scheme. You can support different bandwidth options, data rates, number of users, power and deployment options. You can support from static users like sensors to high-speed mobility scenarios, including maybe not super high mobility, but you can support people or astronauts going in rovers or automated autonomous rovers, or even higher speed vehicles, and you get by default a built-in quality of service framework that enables you to differentiate between mission critical data and maybe not so critical data. So you can have endless opportunities there to optimize your network. In terms of use case examples, and I'll discuss in a minute what we are doing for the tipping point. There are multiple use cases that you can think of. The one that we are focusing at the moment is lander to surface communications on the moon. So you have your LTE end-to-end network deployed on the moon, and then you can support sensors, vehicles, astronauts in the future. You can also considering using the same technology to support extravehicular activities, or even vehicles approaching the International Space Station or whatnot. One key element is that you obviously need to have control over your system from mission control, and that's one of the things that we would be focusing on this tipping point proposal. So what we did last year is that we submit a proposal for topic number 2 on the tipping point solicitation, and it was about the use of LTE 4G for proximity communications on the lunar surface. We are teaming up with Intuitive Machines, so we would be using their Nova Sea lander to take our end-to-end LTE network to the moon. We would be deploying a rover that would carry our LTE user equipment, and we would be testing and verifying the LTE performance of our system next year. In order to do that, obviously, a lot of the work that we need to do is for us to take commercial off-the-shelf equipment that we use in deployments on Earth every day, and harden it to make it ready for operation on the harsh lunar environment. So in terms of our technology demonstration main objectives, that's basically what we want to do. We want to integrate our assets, our LTE network assets onto the lander and the rover. We are gonna soft land on the south pole area of the moon late 2022. Our mission is expected to last around 11 to 12 days during the illuminated time of the period. We would deploy a rover, which would contain part of our LTE equipment, the user equipment, and some of the antennas, and we would establish an LTE network. We would verify the performance of our system, our wireless network, in two main scenarios. One is in short range distance from the lander in the order of 100 to 300 meters. And then we would attempt also a long range testing where we are basically driving away from the lander and checking all the system performance characteristics. We are obviously taking all this information back to ground station via some proprietarily developed operations and maintenance system that works in lossy and high latency links. And all of this is basically for us to enable the advancement of the technology readiness level of the LTE technology, and hopefully paving the way for future missions and commercial opportunities. And in summary, what we are doing is that we as Nokia Bell Labs will provide hardened low power, basically swap optimized size, weight, and power LTE end-to-end solution, which is basically consisting of hardware, software, and all the end-to-end system design, which also includes some RF propagation simulations that, based on the data that we would gather from the mission, we can calibrate and optimize so that then future missions and deployments we can estimate the performance of the system even before we get there. So that's what I wanted to share with everyone today.
Great, thank you so much. That's really exciting. And let's see. So there's a question in the Q&A. How are you thinking to avoid interference with the radio quiet zone?
We are actively working with NASA and NSF to assess the interference, potential interference from our LTE network. What we have estimated so far is that the power levels are so low that we are not causing any issues. There's further studies to be done. One thing to remember is that for this mission, we want to verify it's a short-lived mission, and we want to verify that we can use this technology in the scenario that we want to use them. And then there is the whole discussion that needs to happen in parallel. What would be, for instance, the right spectrum allocation going forward if this technology would be then de facto used in the future. So we are analyzing what would be basically the short impact and the longer term view we also keep in mind.
Okay, great. Thank you very much. Okay, let's move on to our next speaker, Dr. Paul Van Susante from Michigan Technical University. Paul, are you there?
I am here. Can you hear me?
I am.
And you can see my screen?
So. Yep.
All right.
Go ahead.
Thank you. All right. So my talk is about the NASA Big Idea Challenge, which is a student competition that we won. And the topic of that was the Tethered Permanently Shadowed Region Explorer, which we lovingly called TRex. All right, so it was done by a large group of students, and I was supervising them. It went over several semesters, basically 3 semesters. It started in the fall of 2019, and it really just ended here in the spring of 2020. Started, of course, with the first idea, then the writing of the proposal, of course, submission, and then in this case, we got awarded as one of the 8 selected finalists. And then we, of course, started, we got part of the funding, we started our work, and then we did our intermediate report. And then, of course, the final presentation was past January. Of course, COVID happened in between all of this, so it made things quite interesting. And then we were declared the winner on January 8th of this year. So what was the problem that we were trying to solve? So based on the competition, right? So the key is always when writing a proposal is to make sure you address the topic and what sort of NASA is looking for in this case for their request for proposals. So here the problem statement was to design and build, but also test, because we were supposed to get to TRL level 6, lunar payloads that can demonstrate technology systems that are needed for exploration exploration and science in the permanently shaded regions of the moon. So a challenging topic. And so one of the key things that we thought of was, twofold. Basically, what's the most popular spot in an airport when you travel? Well, it's the place where you can plug in your adapter for power, and it is where you have free Wi-Fi, right? So in our case, our rover, our mission idea was that we were going to do that inside a permanently shaded region. So in this case, we wanted to provide power and data to rovers or other missions that would happen inside the PSR. So our vehicle would be a service vehicle where you could then recharge and in this case, you serve basically as the local Wi-Fi hub. Okay, so that's the idea. And to do that, what was our novel ideas here is to, since we are in the PSR, how could we use the harsh environment to our advantage? In this case, the super low temperatures, we were trying to think about not fighting them, but using them to our advantage. In this case, using a superconducting tether would allow us to send large amounts of power down there, as well as data, without any losses, essentially. Now, just to go quickly to our concept of operations, right? So the CLPS lander would land, we would get off the lander, and we would then traverse over the little portion that would be in the sunlight, right? Because the lander could land within a certain distance to the rim, about 125 meter. Then we would start the descent into the PSR. We could continue deploying the conventional tether. Then we would go into the permanently shaded region, but we haven't quite reached the cold temperature yet. And so we have to continue using a conventional, or at least regular tether, if you will. And at that point where we get enough temperature cooling, we can then drop our sort of conventional cable and continue with the superconducting cable. Now, this cable is only 0.2 millimeters thick and can transfer up to 10 kilowatts of power. And the nice thing about this is, because it's a flat tether, the 2 kilometers of superconducting tether weighs only about 2 kilograms. So it's extremely light. You can have long distances and virtually no losses, except for what you have over the conventional, more conventional conductor, basically. Now, once you get down into the crater, the permanently shaded region, we essentially would just park our vehicle, and we would then become a hub where other vehicles that would be, having a mission down on the crater would come to recharge, but also where we could be the communication hub. So those other vehicles would not have to carry large power systems or communication systems to transfer all the way to up to, let's say, satellites or something like that outside line of sight, because our cable would be directly connected to the CLPS lander. Now, of course, the CLPS missions are supposed to only last 1 lunar day. However, there's no reason why this couldn't last longer than that, if the CLPS lander would last longer than that. Now, during this process, we also developed testing facilities. One of those things that was really necessary was to be able to test our mobility of our vehicle to go down into a PSR. So we tested our vehicle up to 45-degree slopes in a basically lunar simulant test bed that we developed our own. We also have gravity offloading systems in our sandbox, so we can essentially take 5/6 of the weight off the vehicle and then go from there. Also, in parallel, I had the dusty thermal vacuum chamber that was coming in, and so we were also preparing to do tests in lunar conditions with simulant in a vacuum for the TRL 6 qualification. Now here you can see a very quick video of this vehicle traversing down our 45-degree slope. This is, of course, sped up so it can fit within the time allotment here. And so we can see here the spool drop and then the further going down while deploying the superconducting cable. Oops. Now, as part of this work, we did a lot of different things. We accomplished a lot of different aspects. We, of course, developed some technology, we developed our rover, and we developed our facilities. And so we started with breadboarding, and we ended up with doing a dusty thermal vacuum test of our electrical system under lunar conditions. We also started off with several different versions of the rover, where we started first with just, hey, does the basic idea work, to essentially a fully integrated version that could be tested in the vacuum chamber. And then, of course, our facility development from a bunch of boards to fully ready, hermetically sealed, with lunar dust filled test chamber. And then at the end, of course, we were very happy to be awarded the Artemis Award by then NASA Administrator Jim Bridenstine. And we also were awarded the Above and Beyond Peer Award and the Fly Me to the Moon Peer Award for those that our peers thought we were the most likely to actually go to the lunar surface. Now, we are, of course, looking into future development of this. It is a very promising technology. We actually did submit to the What's on the Moon competition. We hope to find out in the 20th, I believe, whether or not we were successful. And in the meantime, in the summer, we will continue developing other projects, such as an ESI grant, a LuSTR grant. We're part of Survey, and then we have several other smaller test grants that we work with. And we are certainly looking for industry collaboration to bring this technology up to actually flight level. So that's kind of what we're looking at here. Now, one of the keys of this panel is what makes you successful here. And so one of the things that I found in writing these proposals is that you really need to find a solution that fits the need. These RFPs are written for very specific things, like yesterday was mentioned, follow the instructions, right? So it's spelled out. So you got to really follow those instructions. But you also need to have something that actually fits what people are asking for. And that's a key thing. But of course, you need to have a great team and good partners. So we partnered with several different companies. We've been very successful with that. Then, of course, capabilities to do it and the facilities to do the testing, part of which we built. And then, of course, being in the right time and place to submit something. Like the superconducting cable, for instance, was an idea that I had in 2001 as part of my master's thesis. But at that time, there was no way to get funding to do that. And so now there was, and we submitted it, and we fortunately got funded. So anyway, that's all I have. So if there's any questions, be happy to answer any.
Alex McCarthy from AI Space Factory. Alex, you ready?
Hi, yes, can you hear me okay?
I can, thanks, go ahead.
Great. Let me share my screen. Is that loading okay?
Yep.
Great. Hey, everybody, and thanks for LSIC for inviting me to present this. My name is Alex McCarthy. I'm the CTO at AI Space Factory, and I'm going to talk a little bit about a new project we're working on, which we've dubbed the Relevant Environment Additive Construction Technology, or REACT project. But before that, just a little bit of company background. In 2019, AI Space Factory placed first in the construction portion of the NASA Centennial Challenge. And in doing that, we were printing a 1/3 scale prototype Martian habitat. So the sort of technology that we've championed is a large scale thermoplastic extrusion 3D printing method, in which for this challenge, we had printed with a basalt fiber reinforced PLA polymer. And after the success of that work, we wanted to mature this technology, and definitely in the context of the Artemis program, we wanted to develop the technology further so that we could utilize it for lunar bases in the future. So in 2020, we applied to the NASA announcement of collaboration opportunity, and we were fortunate enough to be one of the awardees for that. So that'll be a 2.5-year project. that we just kicked off this January, and we're collaborating with the Kennedy Space Center SwampWorks group, especially for their expertise in ISRU material development. So I'm just going to go through the top 3 sort of objectives for this project. So the first objective is based on ISRU material development. So our process, as I mentioned, is based on thermoplastic extrusion. So we're going to be, one of the objectives is to compound regolith simulant, in this case, with thermoplastic. And for those not familiar with the process, that basically means using high shear, high temperature mixing to extrude material, cool it down, and then pelletize it into a feedstock that we can use with our 3D printing technology. And the considerations here are, of course, we want to reduce how much polymer we're using. There's a potential, perhaps in the near term, to use recycled mission waste if the polymers from that work out well. I think ultimately we would like to find ways that can be synthesized from local carbon or water resources. And in the meantime, we just want to reduce launch mass, of course, as much as possible. And there's a myriad of other things that we want to optimize for: mechanical properties, withstanding the lunar environment, but I won't go into too much detail there. The second objective that we have is to demonstrate 3D printing under lunar conditions. I think, to my knowledge, this will be the first time that anybody's attempted an extrusion-based 3D printing technology under vacuum and low temperatures. So we're working with SwampWorks that are building a vacuum chamber with low temperature capabilities, and we're going to be building a miniaturized extrusion 3D printing system and trying that out for the first time. And that'll be an interesting challenge because our process has a lot of high temperature thermodynamics going on with it, and we're losing our main heat loss pathway, which is convective cooling. So lots to learn from 3D printing under vacuum conditions. And then our third objective is based on building design. So AI Space Factory has a lot of expertise in architectural design, and we work with structural engineers all the time. And one of the things that we want to do is take what we've learned from the material development process, our material characterization, et cetera, take the information that we learned about the lunar environment through our partnerships with NASA, and design a structure that would be suitable for a moon base. So the plan for this is to design a unpressurized structure that's going to be providing protection to astronauts and mission assets. So that'll be protection from radiation, protection from thermal variation, micrometeoroid protection, all kind of in the context of building a base at the lunar South Pole as part of the Artemis program. Beyond that, we're working with a structural engineering firm to really think about what it means to build a building on the moon, since we haven't done that before. So we're going to be looking at, how do we think about moonquakes in terms of translating those to more typical Earth-based building codes? How do we think about soil conditions in terms of making sure our foundation work is stable, things like that. And then finally, of course, we want to make sure it's a functional space. So of course, it needs to be large enough to hold the things that we want it to hold. But we also are thinking about extensibility, so that as the lunar base grows, the designs we come up with are naturally sort of extensible. And then because it's providing such critical protection to the astronauts and equipment, we want to think about safety and redundancy in case there's ever an issue. We want to make sure that we're thinking about it in that context as well. So I'll leave it there so I don't take up too much time. But if there's any questions, I would be more than happy to answer.
Great, thanks, Alex. That's really exciting. There is a question in the Q&A asking about what facility you're using to test your 3D printing in a lunar environment.
Yeah, that's a great question. So we're fortunate enough that the KSC SwampWorks group is building a new vacuum chamber with low temperature capabilities for us, and we're going to be building a miniature 3D printing system, sort of on the meter scale. I don't have the dimensions off the top of my head, so we're going to be able to take advantage of that new capabilities at SwampWorks.
Okay, great. And I want to thank all of the panelists. This is really exciting, the work that you're doing, and you know, all of these great technologies that are being developed for the surface of the moon. I want to take 1 minute to throw a question out to you all, even though I think we're up on the hour. You know, for some of you talked about the simulants and testing that you're using. I want to ask you all if the simulants you need to do the development that you're working on already exist, or are there any aspects of the simulants that are lacking that you think would really be important to develop so that you can, you know, further test your technologies? So anybody want to take that one?
I'm happy to talk to that. I think think about this a lot. The mechanical properties of any sort of ISRU building material that we make are going to be super critical for safety reasons, obviously. And it's unlikely that we're going to be able to import enough lunar regolith to Earth to get the actual real deal tested here. So at least from our perspective, I think the morphology of the material is probably the most critical for us because it has a lot of implications on how it gets processed and how the mechanical properties are. But I think in the end, we're just going to have really healthy safety factors because there's no way we're going to be able to have as high a certainty as we ever would on Earth. Like it's already a novel building technology and there's so many other certainties. So we're just going to have to live with it to some degree, I think.
Okay, thanks. Anybody else want to take that one? All right. Well, then we are scheduled for a break right now. It's we're supposed to be back at 3:15 Eastern time, and at which point in time we will break out into the breakout session. So thank you again to all of the panelists, and we will see you back in 15 minutes.